I also follow the book of Slocum and colleagues in most of the chapters today. So what are dasymetric maps? Like the choropleth map, dasymetric map uses aerial symbols to represent presumed zones of uniformity. But unlike the choropleth map, the bounds of zones need to match enumeration unit boundaries. So you remember the choropleth map? It was always about this enumeration units. Usually these are administrative areas like provinces, districts, counties, and so on. With dasymetric maps, this is a bit different. So they do not need to follow these boundaries. So it is possible to establish other kind of boundaries in these maps. But what is still the same is these zones of uniformity. So we assume that within these areas, data is more or less homogeneously or dispersed. So we think in the whole area we have the same value. Of course, sometimes we know this is not true, but we have just data for the whole area. And yeah, you will see then what's the difference here. The dasymetric map is used to display standardized data like the choropleth map, but needs unstandardized data, raw totals for each enumeration unit as the basic raw material to start with. So we need other kind of data. We need raw data. To get a dasymetric map, the raw totals have to be redistributed within the enumeration units with the help of ancillary information. Ancillary information is additional information. So, for example, from a more detailed land use or land cover map, or from remotely sensed imagery. This is also a possible source. Here now two maps just to illustrate what is meant with this redistribution. So A is the normal choropleth map we talked about last week, and B now is a dasymetric map. And you see the boundaries are different. Here, the boundaries are the enumeration units. And here, you see the enumeration units, but this is more like a background information. The boundaries of the data, the different areas, this homogeneous data is now different from the boundaries of, yeah, here's maybe counties. So the boundaries of enumeration units with the highest percent area inked are depicted in white to ensure easy readability. This is just if you wonder why we have white boundaries here. It's just because they would be nearly black like the color within, and then you wouldn't be able to see these boundaries. So that's the only reason for that. So this is the idea of dasymetric mapping. And of course, we need more information. How can we do that? So how do we decide where to draw this boundary? As there is no fixed line right from the beginning, we have to think about that in this method. So this here is now the basic principle. The problem is how the raw totals for source zones, usually administrative enumeration units, should be redistributed to target zones defined by the area of overlap between the source zones and so-called ancillary zones. These ancillary zones provide additional information and are spatially more detailed than the source zones. So we have source zones here. These might be administrative units, and then we have more detailed ancillary zones, for example, from a land cover map. And this land cover map tells us more about the distribution of the population, for example. And then if we overlap the two, we create such an overlay, and then we get target zones. These are zones within enumeration units, and at the same time within these ancillary zones. So we get the more precise, more detailed information. This example now is from Corey Eicher and Cynthia Brewer. We see a choropleth map of population density for the 159 county region. It's a county region because it's not just one US state. So here obviously is a border between two US states. It doesn't matter where it is, just you have this typical administrative area setting here. And the task was now to redistribute these raw totals of population density in a way to better correspond with the actual distribution of people in the region. And therefore, they used this data here. These are 580 ancillary zones. And yeah, they use these zones as source for additional information. The additional information used for redistributing the raw totals of population density was taken from a land use land cover data set from the US Geological Survey. The data set split this 159 county region into 580 zones that fell into either urban, agricultural, woodland, forested, or water categories. To assign population to the target zones, they compared three methods: binary, three-class, and limiting variable. They produced densitometric map based on the binary method. You can see this one here now. In this binary method, the land use land cover categories were split into two groups. Therefore, it's binary. Binary is always, it's just two. Also, the binary code is just it just consists of 0 and 1. And here the two groups are habitable and uninhabitable, because we need more detailed information about the distribution of population. Main question here. The habitable group included urban, agricultural, and woodland categories, and the uninhabitable group consisted of the water and forested categories. And you see that this is, of course, only a very coarse rule. It is clear that urban and agricultural are quite different, of course, when it comes to population density and the chance how many people would live there or could live there, and also woodland. So they are treated as the same here. So, of course, therefore, this method is flawed by some oversimplifications. But still, it is easy to be implemented. The final map has some advantages compared with the choropleth map. So you can compare now this final densitometric map with the initial map where you use only the enumeration units. So this was the initial map. And with this additional information that you get from these zones here, from this land use, land cover zones, you can then more precisely redraw the map, and you get this bathymetric map. So this is the idea. And yeah, of course, I'm not talking here about these different methods. Binary is the most simple one. You can work with three classes, or you can try to define a limiting variable. Then you need more information about this variable, of course, so it makes it more complicated. This is the most simple method here, the binary one that is used in this example. The key to bathymetric mapping is the availability of this ancillary information at a finer resolution than the enumeration units, the source zones, for which you have attribute data available. If you have data available for very fine enumeration units, for example, census tracts, and you are constructing just a small-scale choropleth map, ancillary information and the construction of a bathymetric map might be unnecessary because it would not add much additional information. To introduce the basic idea, the binary method is mentioned in this chapter, but there are many better and also more complex methods described in the literature. Just to mention the intelligent bathymetric mapping developed by Jeremy Menis and Torin Hultgren. So if you're interested to study this in more detail. But it is a map type that is not used too often because, if you have the more detailed data available, then it's not so important to do the work and redraw the normal choropleth map. So in some situations, it's a good idea to do that, but sometimes, as it is written here, you just check out if you have a more detailed map, like with the next level of the administrative units, and then you have the better details, and you don't need anything else. So therefore, the method is not used too often. This was this chapter about bathymetric mapping, and I want to go on with another map type, dot mapping. Dot maps are ideally utilized when you have data, also raw totals, for enumeration units, and wish to show that the underlying phenomenon is not uniform throughout the enumeration units. So therefore, it is a bit related to the bathymetric mapping, where the idea is also that you want to improve this drawback of choropleth map. As with many phenomena, we know that they are not uniformly across a whole enumeration unit. And therefore, we need also here more detailed data, raw data, so that we can give a better picture. We create a dot map by letting one dot equal a certain amount of some phenomenon, and then placing dots where that phenomenon is most likely to occur. Dot maps, like bathymetric maps, use ancillary information to create a detailed map of a phenomenon. An example, data on the number of elephants, for example, living in each country of Africa. Ancillary information might be the location of forests and wooded savannas, as well as protected areas, for example, national parks, because it's more likely that elephants are in this area. So we need boundaries of this area And then we can concentrate these dots in these areas. There are two kinds of ancillary information. The first one, so-called limiting attributes. They place absolute limits on where dots can be placed. For example, it would not make sense to place dots representing elephant population within water bodies. So in choropleth map, usually you don't have the information where the water bodies are. So this would be an additional information that can be used to exclude these areas. No dots would be in the water bodies then. Or the second type are related attributes. They are correlated with the phenomenon being mapped, but do not place absolute limits on the location of dots or zonal boundaries. For example, elephants usually live in a certain minimum distance from settlements. So we do not expect them to live within settlements, and they usually have a certain minimum distance. But under specific conditions, this distance might be much shorter. So if they are under pressure because of drought, for example, they might come closer to settlements. So these are no absolute limits. More and detailed ancillary information helps to better delimit the areas where a phenomenon is actually distributed. Example here, we have the state of Kansas, the United States, and this is about wheat harvested there in 1993. And this dot map with dot locations selected by using cropland areas from a land use land cover map as ancillary information. So you have a legend like that one here. Each dot represents a certain number. Here it's 12,000 acres of wheat. And you use this additional information before to delimit areas where more or less likely wheat can be harvested. And there you spread then the dots. Now here we have remote sensing data. So it's the same example, but what you see here in this section, it's just a small area here of Kansas. It's about this county here. And here you have the detailed information from remote sensing. So maybe you have seen this kind of pattern before in remote sensing data. These circles, so these are typically areas that are used for irrigation. So locating wheat directly using remote sensing versus locating wheat based on cropland from a land use land cover map. The upper left map depicts the distribution of wheat within Finney County, so it's just this county here, based on an analysis of 30-meter resolution Landsat imagery. Whereas the lower right map portrays the same distribution, the gray shaded county, based on a 1 kilometer resolution land use land cover map. So for this map that we have just seen in the last slide, a land use land cover map was used, and this map had a 1 kilometer resolution. Now here, for this county, we can compare this with much more detailed data. So this is just a 30-meter resolution compared to 1 kilometer here. And of course, then you can even better distribute the dots. But you still see that the dots, they're distribution within the county reflects that this area here, here are 2 dots in the county, here are 3 dots in this area. So these 3 dots, maybe they would be rearranged a bit based on this data, but all in all, it's relatively good. It relatively good reflects the actual distribution of the area where wheat is harvested. But this is a good example to see how this basically works. So you need more detailed information, and based on this detailed information, you can then decide where to put the dots in your map. Dot size, how large each dot is, and unit value, the count represented by each dot, are important parameters in determining the look of a dot map, of course. So dot size, you should keep in mind that 2 small dots produce a sparse and insignificant distribution, while 2 large dots give an impression of excessive density. So therefore, we have to find a kind of middle way that avoids these 2 problems. And the unit value, too small unit value, produce a map that gives an unwarranted impression of accuracy. So the impression then of accuracy is higher than it really is. So we should always think of the level of accuracy that we can get from certain data, from certain resolution of the data. A too large unit, on the other hand, results in a map that lacks pattern or character, because then you have only a few dots and you cannot really analyze any pattern. So that's the problem then. As a rule of thumb, dots in the densest area should just begin to merge with one another. So begin to merge means that they are so near to each other that there is no distance between them, then they start to merge. So this is something we should take care about. After calculating the number of dots associated with each enumeration unit, the dots have to be placed on the map. Traditionally, there are 3 approaches for placing dots on the map. The first one is uniform placement. Dots are placed uniformly but with a random component throughout the enumeration unit. But this in fact simulates a choropleth map. Geographically weighted placement is the second method. Dots are weighted toward neighboring enumeration units of higher value. So this simulates an isopleth map, a type we will talk about later today or next week. Geographically based placement is the third one. Here dots are located based on ancillary information, albeit using the uniform approach for areas within which dots are supposed to be placed. This is the preferred approach as it takes advantage of geographic knowledge and produces the most detailed dot map. And this in fact simulates the just discussed decimetric map. And now you can see the differences in these examples. This is the first approach. Now we talk about soybeans in Kansas. And for the dots should be placed in each enumeration unit in a relative uniform fashion. Neither perfect uniformity, because it looks too unnatural, nor pure randomness, to avoid unrealistic cluttering or clustering or any strange gaps. Both is not desired and should be avoided. But you still see that here obviously are county boundaries. So you see a change in the density because within each of these enumeration units, and the enumeration units here are counties, the dots should be dispersed and distributed uniformly. So that's then a possible result. The next one is the geographically weighted approach. And this approach takes advantage of the notion of spatial autocorrelation. That means that high values tend to be located near other high values. This reduces the effect of county boundaries in the map. So if you compare this one with the last one, now it's more difficult to see county boundaries here. So here a bit, but it's much less obvious than in the example before. And the last one is the geographically based method. The most detailed dot map is the result then. And but here additional ancillary information is needed. And the design process, therefore, is much more complex. And you need additional data. And then you, based on this data, you have to redistribute the dots. So it reflects more a decimetric map. Of course, this looks best, the best version of the three, but it depends if you have an automatic algorithm, an automatic method that you can use to distribute these maps. So these examples here, as you see, they are drawn by hand. They are a bit older. It's here, of course, to illustrate the different methods. What's missing here is the legend. So there is no information about how many soybeans are represented by one dot. This information is not there. But yeah, I guess, or I hope you have an impression what is meant here with dot mapping and with these three methods of how to distribute the dots on the map. Then let's move on to the next mapping method. This is a bit longer chapter or section, the proportional symbol mapping. Proportional symbols can be used for two forms of point data. The first one, true point data, actually measured at point locations. Examples are temperatures at weather stations, discharge, spring, and so on. So these are really point, it's really a true point data, so they represent data that is somehow connected to a point. But there are other kind of points, so-called conceptual points. These conceptual point data is collected over areas or volumes, in fact, but the data are conceived as being located at points. For example, the centuries of enumeration units for purposes of symbolization. There are many examples for this. One is a number of microbreweries and brew pubs in each state of the USA, because this is the example used in this chapter, or one of the examples used in this chapter. Some data are not easily classified as either true or conceptual. For example, data associated with cities are collected over the areal extent of each city, but the data normally are treated as occurring at point locations because at typical mapping scales, cities are depicted as points. An example would be number of out-of-wedlock births to teenagers in major US cities. There are also examples about this in this chapter. Proportional symbols can be divided into two basic groups. The first is about geometric symbols. So we can use circles, squares, spheres, cubes, and so on, which generally do not mirror the phenomenon being mapped. Best choice are circles, because they are visually stable, are naturally located at their center, and conserve map space. But bars have the advantage to better represent quantities. Remember, we talked about that. So which symbols are best used, or which aspects of any kind of graphical configuration is best used for representing quantities. And we talked about that. For example, angle is better than area, but with angles it's difficult to use this variable within a map. So quite often we end with area and with circles to represent quantities. But in fact, it's better to compare length instead of area. So sometimes bars are used, but they have the disadvantage that it's more difficult to locate them, that they need relatively larger or more space than circles, which is sometimes a problem if you have great differences between within the data. So some areas have very low numbers, other areas very large numbers. Then you quickly get into troubles when you use length. The area works better for this reason. And the other group are the pictographic symbols. Heads of wheat, caricatures of people, small animals, etc. So shape is used then to represent something in a pictorial way, some object. So they generally do mirror the phenomenon being mapped. Therefore, their meanings are interpreted more easily. They also often act as eye catchers, so they look nice. People like to look at that. I'm more interested in taking a closer look if they see such maps. But it is more difficult to judge the relative sizes of irregular pictographic symbols, especially when they overlap. So they have this clear disadvantage. The first example here. So we have a proportional symbol map. This one here is unstandardized. And we map here conceptual points about microbreweries and brew pubs in the United States. Here, proportional circles represent the raw number of microbreweries and brew pubs in each state. So each circle represents one state and is approximately positioned in its center. So it does not refer to the exact location, it refers to the whole area. Therefore, we speak about conceptual point data. The data refers to an area, but of course you need a point location to place them. So they naturally, the reference point is in the center of a state, but the data is about a whole state. Therefore, it's conceptual point data. The data are unstandardized, and therefore the number of microbreweries and brew pubs is likely to be greater in more populous states. So as you might know, states like California is much more populated than one of these states here in the Midwest region, I think is it called. So these areas here are sparsely populated, and so it might not be a surprise that you have less such kind of small breweries called microbreweries and brew pubs in these areas. So this is the problem with unstandardized maps. So we talked about standardization, and it would be better to standardize the data here as well. And you have here the legend. So the different sizes of dots reflect a different number of microbreweries and brew pubs. And yeah, of course, we all checking out proportional symbol maps quite often at the moment, because there are many maps about the spread of the new coronavirus, SARS-2. And many of those maps are proportional symbol maps. And unfortunately, most of them are unstandardized. So they don't give us the information how many people are living there. They just give us absolute numbers of infected people, for example. And this makes it more difficult to compare. Like in the US, you know, New York State here is one of the highest infected area. In the meanwhile, it's the area with where most or the highest number of people died, unfortunately. But it's also an area with a very high population. So it's necessary to put this in perspective and to standardize the data. Otherwise, you cannot really compare it. Both is interesting, of course, with infections, because the absolute numbers tell us about how fast the virus is spreading. But still, we need a standardization to get a better feeling about the real situation there. Now, this is the standardized map, and you immediately see the situation is quite different now. It's the same data. So we are mapping conceptual point data. It's again microbreweries and brew pubs in the United States from 1996. Here, proportional circles represent standardized data. The number of microbreweries and brew pubs per 1 million people in each state. Again, each circle represents one state and is approximately positioned in its center. And the interesting thing is, of course, to compare the two maps. So some circles are larger now, others are smaller. Of course, where the absolute population is low, the circles now, they are larger. But in areas with a very high population, the circles are lower, are smaller. So we get a much better picture now where microbreweries and brew pubs are more common feature and where they play a less prominent role. So just compare here California. When I go back, this is the unstandardized map, and this is the standardized map. Of course, we have a different legend now, because now we have the number per 1 million population, while here we have the absolute numbers. So to get an impression and to better compare or analyze the pattern of the phenomenon, you usually always need standardized maps or standardized data. Now this is a choropleth map you can use to compare with the other one. So of course the same data. Now here a choropleth map represents the standardized data shown in example B. So the map in the last slide is now here realized as a choropleth map. Now compare these two. The unclassed proportional circles allow for more detailed comparison between the standardized numbers, while the choropleth map gives a better overview. Other advantages of the choropleth map are numbers are related to areas, and they are also represented as areas. And you have not the problem with visual clutter in the northeast. So northeast is here, this area of the states. I go back. Here, you have visual clutter. So if many of these symbols overlap, then it's more and more difficult to see the single symbols. And what's the larger problem is, if you're not really familiar with this area, like me, you get into troubles to know which circles represents which of the states. Because I don't know where exactly are the boundaries of the states now, you cannot see them. And when you look at such a map, you see points. But as these are conceptual points, they represent areas. So here points represent areas. And the advantage of the choropleth map is here area represent areas. Therefore, it has more advantages, in fact, to use the choropleth map. But of course, it's also a disadvantage or an advantage for the proportional symbol map. Here you can better compare the sizes, because here, remember, what's better to represent quantities. Here you can compare areas, which is better than comparing different color values. Of course, you have only these 5 color values here, these 5 gray values, and here you have many more sizes of the dots. Therefore, this reflects the data better, and you can better compare the quantities. So this is an advantage for this map. So it also depends what's your goal with the map. What do you want to show? In which way you want to use the map, for which audience, and so on. And another example here of the same data. Now we have, again, conceptual points, but pictographic symbols are used. This beer marks in different sizes. And here again, it's the unstandardized version, so you would have to compare it with the first map, with the unstandardized one. But here the data is classed, because a continuous continuous scale here for the data is not a wise decision, because you cannot see these small differences. So it's better to have only these 5 fixed sizes of the beer mark, representing certain value ranges here. Otherwise, the map cannot be read. The size of beer marks was just chosen by eye, so just 5 different sizes that can clearly be discriminated. And you can compare this map with the first one in the above series, example A. The design of this map here might be more appealing, but the visual clutter in the northeast here, this area, this visual clutter, is more impeding the ease of interpretation, while the proportional circles in example A are unclassed. This is not really an option for pictographic symbols, as small size differences are harder to be discriminated. I just talked about that. So I go back to the first one here, A, example A. This is the same data, but you have a continuous scale, data scale here. So these circles here, they just represent this one number. And of course, you have circle sizes in between, like that one here. would be in between here, and then you have to estimate the number that corresponds to that one. And the visual clutter here is not, the problem is not as big as with the beer marks. Here, this it doesn't look good. Sometimes you can even not really see that these are beer marks, and it's difficult to locate them also in the different states. Yeah, it's break time. First break. So, yes, I also want to thank you all for handing in your homework, the second homework in time. So I got all your presentations or visualizations, your examples and your texts, and we'll check them during the next weeks. So thank you for that. And now let's continue here with the proportional symbol maps. Now this example is about the out of wedlock births to teenagers. So if you wonder what that is, what are out of wedlock births? So wedding, this term is a bit hidden here. So these are births of teenagers that are not married, unmarried teenagers. And yeah, you see this distribution, the numbers here in this map. The mapping data collected here over areas, cities, that can be conceived as points. So this is for this kind of data. So they are all from cities. Here, proportional circles represent the raw number of out of wedlock births for US cities with a population of 150,000 or more. Each circle represents one such city and is approximately positioned at the location of this city. So it's also kind of conceptual point data, but here, due to the scale, the cities are usually represented as points. So therefore, it's more realistic or more intuitive than representing a whole area by such dot symbols or circles. The data are unstandardized here, and therefore the number of out-of-wedlock births is likely to be greater in more populous cities. So the big cities like New York or Chicago or Los Angeles, you see immediately these are the largest circle. The reason is the data is unstandardized again, and yeah, it's then difficult to analyze this phenomenon. So it's better to use a standardized map. In this example, we have still unstandardized data. Here, proportional circles represent the raw number of people living in US cities with a population of 150,000 or more. So here you have just the population. You can compare this with the out of wedlock birth data. Each circle represents one such city, and is of course then approximately positioned at the location of the city. The data are also unstandardized, and comparison with the map in the last slide reveals a strong visual correlation between them. So again, we have New York, Chicago, and Los Angeles here as the three largest cities. So it's just a population map. And here it makes more sense to use an unstandardized map, because the area of the city is usually not what we are interested are. We are interested in the number of people living in this city, no matter if the area where the people live is larger or smaller. Sometimes we're interested in population density in cities, and of course we need to take into consideration the area. But usually we ask where are the largest cities, and we don't care about the city area. But here it's this map is shown here to be compared with the last one. So I go back one slide and back and forth, just that you see this correlation here. There is a difference when you check out Chicago, for example, and compare Chicago and New York. So here the two circles are more similar than in the population example. So obviously there is a difference here in the data about out of wedlock birth. Now in the next slide, you see the standardized data. And you immediately see a different picture here. Of course, we have the same data to be compared. Here now proportional circles represent the standardized out of wedlock birth percentage of all births in US cities with a population of 150,000 or more. So each circle represents one such city and is approximately positioned at the location of this city. This map looks quite different to the first one in this series, example A, mainly because of a much narrower range of data, which also reduces the discriminability of the circles. So the problem you see is that the circles are too similar in size. So obviously the difference is not that big between different cities. There are, if you compare the largest one with the smallest ones, you clearly see a difference, but many circles are of similar size and therefore reflect that there is not such a big difference here. An important step during the design of proportional symbol maps is the scaling of the symbols. There are three main scaling methods. The first is mathematical scaling. The second is perceptual scaling, also known as psychological scaling. And the third one is estimated scaling. While the first two are usually used for unclassed maps, the third one is mainly used for classed or range-graded maps. First, the mathematical scaling. Mathematical scaling sizes areas or volumes of point symbols directly proportional to the data. For example, if a data value is 20 times another, the area or volume of a corresponding point symbol will be 20 times as large. So you have the same relation. Mathematical scaling is the most often used method for unclassed maps, because this, of course, is easy to implement. Formulas for three often used geometrical shapes are as follows. This one is the formula for circles. This one is the formula for squares. And this one is the formula for bars. So again, you don't need to learn these very simple formulas. If you need them, you will find them. It's easy also to just check them out and remember them if you like, but it's not necessary to learn them for the final examination. At first, the size of the largest symbol is defined. So this is the way it is done always then. So the first is the size of the largest symbol based on the given mapping context. Mapping context, for example, do they refer to conceptual points? How large are the areas? What about the differences within the data? So how large is the difference between the largest and the smallest symbol? These are all the things you have to take into consideration. Afterwards, the formulas can be used to calculate sizes of all other symbols. More interesting, more difficult is the second option, perceptual scaling. Numerous studies have shown that the perceived size of proportional symbols does not correspond to their mathematical size. Rather, people tend to underestimate the size of larger symbols. I will show you that on the next slide. Results from mathematical scaling might be modified or corrected to account for underestimation. This process is known as perceptual or psychological scaling, and it is also used for unclassed maps. Although respective formulas exist, results are not entirely satisfactory. The main reasons for this situation are a too large variation in spatial map context, in map users, and in map use tasks. So there is not one single ideal formula that you can use. In fact, you have to use then different formulas depending on this context, which makes it more difficult. So what is meant here? If we compare in this example, we compare mathematical scaling with perceptual scaling. In mathematical scaling, the areas of the circles are constructed directly proportional to the data. So mathematical scaling, this represents 10, this represents 200. So the area of this circle is 200 times smaller than the area of that circle. This is mathematical scaling. So that's quite straightforward. In perceptual scaling, the size of the largest circle is increased. Here using Flannery's exponent, this is one method, to account for underestimation. So in fact, in viewing the larger mathematical scale circle, this one, most people would estimate it to be less than 20 times as large as the smaller circle. So if you show people these two circles and they should estimate the difference, so what's the difference between the two? Most people think it's less than 20 times. And therefore they underestimate the size of this circle. And to correct for this underestimation, the circle is now larger in the perceptual scaling. So, but for most people, the perceptually scaled larger circle should appear closer to 20 times larger than the smaller circle. So this is the idea, that if people estimate the difference between these two, they come nearer to 20 times than here. And therefore, perceptual scaling improves the situation, because what we always have to take care about is the impression and the interpretation of the users of the maps or the visualizations that we produce. This is most important. Therefore, of course, it would be better to use perceptual scaling. But as mentioned before, there are troubles. It's not so straightforward. There is not just one single formula that works in every situation. Unfortunately, we don't have that. So for perceptual scaling, most empirical studies deal with the resizing of circles. So this is one of the problems, of course. We have different kinds of geometric symbols. For example, circles are most common. Therefore, most of the studies deal with circles because they are often used. Yes, they're the most common ones. And underestimation of sizes is typically more pronounced with circles. So this would be another disadvantage of circles compared, for example, with bars. So with bars, this works better than with circles. A corrected formula for circles developed by James Flannery. It's that one here. So you see there's a difference here in the exponent. For squares, a corrected exponent of 0.54 was derived by Crawford, 1973, indicating that squares are estimated better than circles. So this exponent is different when you use, for example, squares instead of circles. For circles, it's 57. For squares, it's 54. There is even no need for correcting the length of bars. Therefore, remember, length is better to represent quantities than area, but bars are difficult to associate with point location. We talked about that before. But you see here, you don't need a correction for bars. Bars estimation, when it comes to estimate differences between bars, this works much better, and no such correction is necessary for bars. Now let's check out an example. There's again the microbreweries and brewpubs in 1996. So here now we have mathematical scaling in this example. And now we have perceptual scaling based on Flannery. Note that perceptual scaling appears to have little effect on the overall pattern when the largest circle on both maps is the same size. So I go back and forth again. So the largest one, it's the one in California, is the same. Therefore, the correction is for the smaller ones. The smaller ones become smaller in the corrected version, so that the difference is larger between the larger ones and the smaller ones. The third method is the estimated scaling. Estimated scaling is mainly used for range-graded maps. Range-graded maps are created by classing the data and letting a single symbol size represent a range of data values. So one size for each class. One size represents several of the data values. Sizes of range-graded symbols normally are selected to enhance the visual discrimination among classes. An example is the set of symbols developed by Gordon Dent, 1999, based on his experience in designing maps. After determining the number of value ranges of classes, the largest and smallest symbol are selected and then intermediate sizes estimated. So these are potential circle sizes for range grading developed by Gordon Dent. It's just based on his practical experience. And here we have an example, range-graded map using squares as proportional symbols. So now squares are used, not circles. We have again the microbrewery and brewpubs example. To create this range-graded proportional square map, distinctly different small and large squares were selected. And then 3 intermediate squares were specified so that their areas were evenly spaced between the smallest and largest squares. All sizes are therefore the result of estimated scaling. So there is no direct proportion. You don't need any formulas here. This is just done in a visual way. So the largest and the smallest squares represent these respective classes here. So for all numbers 3 to 10, you have just one size here. Therefore, it's a range-graded map. And then for the next class, you have another size. And you define the smallest and largest first. Of course, then you have to check. The largest should not be too large, that it covers your areas that are represented here. We have conceptual point data here because you have a point location for the symbol, but this symbol represents the whole area, here the whole state of California, and it's just located near the center. So here, of course, the center would be nearer to the square of California, but then it's moved a bit. Also here, it's more cluttered. You have to move the symbols, so readability has to be ensured. This is, of course, important. So you define the smallest and largest, and then you define sizes in between that reflect the numbers in the classes. And so they should be easily discriminable. And so that the relations fit roughly to the numbers. So it's just estimated visually. It's not computed. And the smallest circle you have here, 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 and so on. The next smallest one is that one here, 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 here. And the next larger one are the circles, I see, the squares here. And then you have the second largest. You have it here in Texas, for example, and then the largest one, which you have only in California. Advantages and disadvantages of such range-graded maps. Advantages are symbol sizes are more easily discriminated, and matching map and legend symbols is ease, therefore. Contrast in circle sizes might enhance the map pattern. Also square sizes, of course, better suited for pictographic symbols. So it's the same basic idea as we had in the example with the beer mugs, with these pictorial symbols. There you have a certain number of fixed sizes, and each of them represent one class. So each size represents several numbers, and all these numbers lie within one class. The disadvantages are misinterpretations of represented values are possible. More pronounced size differences potentially create a pattern when there might not really be a meaningful pattern. For example, for a data set with minimum and maximum values of 10 and 11% respectively, range grading would create obvious differences among circles, even though a 1% difference might be of no significance. So again, it's possible to produce a map, and it looks like there are great differences. But the data behind the symbols is not that different. So this is also about the responsibility of the map maker or visualizer to think about what we are doing. So we are responsible for our visualizations, that they are useful and that they reflect the data in a responsible manner. So now We have again the example with the out of wedlock birth to teenagers from 1992. Now it's range graded here. So range graded means you have these 5 classes here, and for each class you have a certain symbol size. The standardized data is presented by range-graded circles. Their sizes are based on dense 5 smallest circles, which cause too much overlap in this map, by the way. But it's just an example to show you how we can, of course, manipulate also the maps. Note, 2 circles are marked with S here, S and T, to show potential risk of misinterpretation. For example, a reader failing to examine the legend might say that the value of circle T is considerably about 30 times larger than the value of circle S. So if you compare this small circle here and this large circle here, you think the difference is about 30 times. But the numbers specified in the legend indicate that the values differ by only a factor of about 4. So if you check out the numbers here carefully, then you will see this is not the case. So it's this class here for S. S is Salt Lake City, and T, I don't know, it's Tacoma, or I'm not sure about that city. But the point here is you have here quite small number from 3.3 to 6.9% of all births are out of wedlock birth to teenagers. And this circle here for T is between or from 13 to 16%. So the difference is much smaller than the sizes reflect the sizes of the circles. Therefore, this is misleading. You should keep that in mind, how we use the size differences, how we define these steps here between the numbers. Now this here is the same data. The standardized data is represented by mathematically scaled circles. So this is not range graded. You see the circle sizes. Each size now represents a certain number. So you have also in between sizes, not just these 5 here in the legend. They just represent certain numbers as examples. But you have numbers in between, and therefore you have also sizes in between. And this here is mathematically scaled. So you see now the difference between these two. It's just about 4 times. If you think about, I go back between S and T. It's the same data. And you see how different the two maps look. Range graded here with this kind of sizes defined, and here mathematically scaled. Now, an aspect of proportional symbol mapping is also legend design. One question is about how to arrange the symbols. So nested legend arrangement is one option. Here, smaller symbols are drawn within larger symbols. You will see an example a bit later. Or linear legend arrangement. Here, the symbols are placed neighboring each other in either a horizontal or a vertical orientation. Number of symbols to be included, that's another question for the legend design. So in classed range-graded maps, the number of symbols in the legend is a function of the classes displayed on the map. So of course, if you have, for example, a 5-class map, you will have 5 legend symbols. because there are only these 5 sizes. In an unclassed map, it's of course different. So you can use different kinds of scaling, for example, mathematical or perceptual scaling. One option is smallest and largest symbol actually shown on the map, and interpolation of intermediate size symbols, as many as appear to be easily discriminated. Or using symbols that represent round numbers and are good representatives of those appearing on the map. This is another option. Now here you see these differences. These are examples for various legend arrangements. A and B, these are nested versions, so the smaller ones are within larger ones. This is meant with nested. You can write the numbers within or outside of the symbols. C and D here are linear horizontal arrangements. E and F are also linear but vertical arrangements. It is also possible to reverse the sequence. That means to start with the smallest values at the top, especially for range-graded maps. So here the largest numbers on top, but you can also change that. We read from left to right, and therefore we start usually with the smaller numbers on the left-hand side. But here, of course, it's not a rule, but one recommendation in legend is that the larger numbers should be on top. But of course, this looks a bit visually unstable to have larger circles above smaller ones. So there are arguments for reversing the order. It also depends a bit on the topic. So what kind of numbers are shown here? Is this about population or certain population groups? Or does it have another meaning? So sometimes there are meanings that are positive or negative. And maybe you want to start with the positive ones, or you want to start with the negative ones. This might also be an argument for one or another solution. Another question with proportional symbol maps is how much overlap should be within these maps between the symbols. Small symbols cause little or no overlap, and thus the map with weakened spatial pattern. Large symbols, on the other hand, create a cluttered map, making it difficult to interpret individual symbols. So again, we should try to find a middle way to avoid the negative consequences of the two extremes. Somewhere in between is a good solution, therefore, but there is no rule. There is no exact rule how to produce optimal symbol overlap. Symbolizing overlap is also an option. So overlap can be symbolized with opaque or transparent symbols. This is also an option. Another option is the use of redundant symbols. So where you use different variables to express the same aspect of the data. Here is an example for too much overlap. You have, again, the microbreweries and brew pubs. And this is about the effect of varying circle overlap. So this map is too crowded. Even here in the legend, you get into trouble. So this is the southern tip of Florida. Of course, this is not a good solution. It covers too much space of the map. Even not only here in the Northeast, where we are used to problems with overlapping and visual clutter, but even here in the Northwest, it's more difficult now to see where are the boundaries of the administrative area, the states here. So this is not a good solution. It's too much. And this here is not enough. But it's the other extreme. So the map appears to be empty, and it's more difficult to analyze the pattern here in this area. And something near to this solution would be seen as an appropriate overlap. But this is the first variant, and this is the second variant. I go back. So you see, of course, you have a range of good solutions, let's say. There is not just one. And yeah, it depends. If it's important for you to reduce the visual clutter here compared to here, the differences between the circles are more pronounced than here. So in the first one, it might be easier to estimate the differences between the circles. Here you have a better solution with the visual clutter. So the visual clutter is reduced in the second variant. Now, the other thing just mentioned is about this how to deal with the overlap situation. So it's possible to use a transparent solution where you can see the circle. That's a rule. In fact, the larger one should always be more in the background. So the smaller the circle, the nearer the circle is to the viewer of the map, to the map audience. So you draw the smaller ones on the larger ones, which is just logical, because if you draw this one behind the large one, you cannot see it. In this solution here with transparency, yes, you can still see it. But here with the opaque method, you would not see it. This is also something that we expect, that no symbols are hidden behind a larger circle. So there should never be smaller circles hidden behind the larger circle. Always put the smaller ones above the larger ones. And of course, in this method here, you have more lines. This one looks clearer. From my point of view, this B solution with the opaque method is the better one. It's also the one usually used. Personally, I do not remember that I have ever seen a map that used this transparency. Of course, if you have here, you have just black and white map. If you have gray values in between, then you can maybe handle this in a bit different way. But be careful, because if you reduce the color value, then of course it also looks like the value represented is lower. Therefore, it's better to have just the variable of size here. We will see in the next example that this otherwise it might cause problems. So here now we have the use of redundant symbols on proportional symbol maps. So redundant means you have not only the size, the area here of the circles, but you have also the color value. We have again the data from the out of wedlock birth to teenagers from 1992. It's a standardized map, so we have percentage. It's also range graded, because one size is chosen to represent a whole class of values. Therefore, it's range graded. And here the visual variable size and value are used in a redundant way to make it easier for readers to differentiate between the overlapping symbols. But again, it has this drawback that something not only looks smaller than it, also it's weakened because it's not that black. It's nearer to the background, and therefore this additionally adds to a difference in the impression. It works here because we have a range graded map. Therefore, we just need 5 different representations of the 5 different classes. And so the sizes should be clear distinction in the sizes, and additionally, we have a clear distinction in the color values, which raises our impression of difference between the classes. But we have another problem here that we talked about before, that the difference is too big. So remember S and T, this example of these two. If you estimate the difference here, it might be 30 times, but in fact, the numbers are much smaller. And this problem that we had before is now even larger because this is white or near to white, and this is much darker, which adds to the impression that the difference between the two is very, very large. But the difference in number is not that large. So keep that in mind. It's not a bad solution, but it's also not the best because of this drawback from my point of view. Sometimes you want to exaggerate differences, give a more pronounced picture of the differences, so to clearly show where are low numbers, where are high numbers. But it's also important to avoid misleading the audience, the map readers, and to clearly, for example, in some text information, to make clear where is the range of differences here, where are, for example, the highest numbers and where are not, where are the smaller numbers, and what about the differences and the reasons behind that, to help the readers to interpret the map in the right way so that they are not misguided by the visualization. That's the end of this section, and it's also time for our second break before we continue with the next map type, the flow maps.
播客的列表，还有这个
So I'm back again. Sorry, I'm a bit late. Then let's continue. Flow maps. That's another type of maps. Flow maps depict the movement of phenomena between geographic locations. That's the general description. Typically, lines of varying width are used for quantitative data and different color use for qualitative data. Flows are usually between points or areas. If they are between areas, often conceptual point locations are assumed for origins and destinations. Flows can be along real-world lines, for example streets, or conceptual lines, just connections with assumed locations which do not correspond with any real-world lines. Five types of flow maps can be discriminated. The first type are distributive flow maps. They depict the movement of commodities, people, or ideas between geographic regions. They often show so-called working lines. I will show you that in examples. Network flow maps, that's the second group, depict flows within networks. The third, radial flow maps, have a distinctive radial pattern. The fourth, the continuous flow maps, depict the movement of a continuous phenomenon, for example, wind or ocean currents. And the last one are telecommunications flow maps. They depict the movement of information, for example, in the internet. Special case of a network flow map. So now I show you some examples. This is an example for the African slave trade in the mainly in the 18th century. So you see the numbers. Millions of people have been forced to leave their country. They are brought as prisoners to other parts of the world, to the New World, as it is often called in the European history. And people are sold like goods and forced to work on the fields or in mines, wherever. And this is an example for these forking lines. So that means, there are divides, people coming from different areas. In this case, they unite in one arrow, but then they separate again because they're distributed to different places. That means some are coming from here and distributed to this area, some coming from here distributed to that area, and also from here to this area, or from here to that area. So this is all possible. And also even here from Eastern Africa, there is a smaller part that also adds to the numbers. So this is a distributive flow map with forking lines. This now is a network flow map with radial components. It's about world air travel. So of course you have this, you have even conceptual areas in part here, not only conceptual points where the arrows point at. So here, for example, it's just water, so they just show the direction. So it's a more general overview about the most important flows of air traffic. Also here you have this conceptual point location. This is also about air, but this is about global airline traffic trends. So it's a scenario, a model, a simulation of what will happen in the near future. But it's an older map, so the future here means the time from 2010 to 2011. And this is also a network flow map. And these conceptual points, they just represent larger areas. So for example, here, North America. So it's somewhere near the border between Canada and the US. So here is no main airport. This is just reflects the whole area of Northern America. Or here, for example, it's, I don't know, maybe this is near Shandong, but this reflects the whole area of Central, Southern, and Southeast Asia, and so on. That's a nice one. These are the flight connections in the area of the Pacific, so between all these small island countries in 2017. It's also, of course, a network flow map, but here you have qualitative data. That means different colors, different color hues are used to represent the different airlines of the different countries. Some of the colors are a bit hard to discriminate, but overall idea is interesting, so you have an overview about all the flight connections in this area. Or here now, this is about quantities. The average daily road traffic in Switzerland, 2007. So that's the network flow map, and the width of the line, as you see here in the legend, this is German and French. And as you know, there are four official languages, but three main languages in Switzerland, German, French, and Italian. So there is no English version here. This is German and French. Here, by the way, you have the four languages. So this is the name of Switzerland, the official name in the four languages. Or another one, also a network flow map. This is about the annual freight tonnage by mode in the US. So mode of transport means there's a difference here between the road system, the railroad system, and the waterways. These are the three different modes of transport in red, brown, and blue. So here it's about the freight transport. So also quantities represented by the width of the lines. Or that one, that's planned. I don't know if it's a wishful thinking or if it's really something that will be realized until 2050. It's a bit of that what China already has, a very good network of high-speed connections. So this is a development in this direction in the United States. So these are possible. So it's not actually planned in that way. Some more concepts, potential concepts for the future. So possible trans-American passenger network in the United States. And you have here also qualitative information, the different colors for the different regions mainly. But you have also ordinal data because you have these different classes here, ranked classes of the high-speed rail, this is the SIG line, or an incremental high-speed rail, that's a bit smaller line, like here, or you have a long-distance corridor line, which is then maybe not that fast. So you have different classes, represented here also by width of line. Or that one here, this is about import and export from the United States. So imports from and exports to the United States, based on the 15 most important trade partners in 2011. And this is a radial flow map with conceptual point locations within the countries. So of course, here, for example, this arrow points towards Brazil, but it's not a big city or something like that. It's just the arrow is connected or points towards Brazil. That's all the arrow is saying, because maybe here is the name of Venezuela for this area, and therefore the arrow points to this area of Brazil and not here in the center, because they wanted to place the name here. So that's not important. In fact, it's just that the arrow shows or points to the right country. That's a nice map, but the topic is not so nice. This is about foreign fighters that travel to Syria to fight there. It's about the war in Syria and about from where the fighters come, 2013 to 14. It's also a radial flow map. We can say it's a distributed flow map with a distinctive radial pattern. And additionally, you have also forking lines here. But compared with the forking lines of the slave trade before, you see that several arrows join to form one big arrow, but they do not split again because they all have the same, they all point to the same country, to the same area. So forking here is just on one side of the arrows, not on both sides. And again, we have these conceptual points. So there's one point here in Russia, but of course, this is for the whole of Russia. Most fighters maybe come from this region because here the Islamic religion is more dominant within Russia. So sometimes this plays a role, sometimes not. So sometimes it's just, for example, here, the line simply starts in Germany, no matter where in Germany, it doesn't matter. Then here are very beautiful examples. You noticed, I guess, that I used one of these visualizations as background for my title page for this course. I have added here some links that you can check out. You will find more information there. Also, this one is very nice, the third link, because this is historically, it's the first example with this kind of depiction. It's a black and white map about the US, and also a very beautiful map that I can highly recommend to you to take a look. We have the global wind patterns here, and these examples that I show to you are made by Cameron Beccario. These are excellent examples of a continuous flow map. And this continuous flow, this is the background. You have an animated map. You have also color coding here for additional information. And the idea of this method is quite old. So if you check out the historic examples from the, I think it was in the first class, the first lesson that I gave to you, the examples I've shown, there is one black and white map where this idea, in fact, is already implemented, but of course not as an animation and not with such fine elongated lines, but the idea to have smaller lines that are a bit thicker at the arrowhead. They're not arrows, but you have a kind of arrowhead that points in a certain direction. And now this is animated here. And yeah, it gives us a very good feeling about the content, and it also looks beautiful. Also here are these global regions. There is information about the different height levels above ground, so wind patterns near the surface or far away from the surface. This might be temperature, the color code, temperature of the air flows. Or here, that's a hurricane or typhoon near to Taiwan or between Taiwan and Philippines. You see the wind speed in this here near the center is much higher than outside. Another example now about the internet. So this is the worldwide internet traffic on the NSF net. NSF is the National Science Foundation, and that's a quite old situation here. That's the backbone of this network in 1993. And it's a telecommunications flow map, or a kind of abstract network flow map, you could also call it, with real-world point locations. So these are the points where the servers are, the connected computers, and color represents the activity of different links. So red depicts heavy traffic, so from some parts of the US, for example, to some parts of Europe. Or even more abstract, this is the spatial map of the internet based on data found on the site opted.org on 5th January 2005. It's a telecommunications flow map, also a kind of abstract network map depicting qualitative and quantitative data with conceptual point and line location. So as you see here, this area, the small area, is enlarged here, and then you have the IP addresses, the actual IP addresses of computers here. And the colors also have a certain meaning. And each line is drawn between two nodes representing two IP addresses, as you see the enlargement. The length of the lines are indicative of the delay, so the time between two nodes. So if the line is longer, it takes more time to send information back and forth along this line. Color codes are used for domains. So these domains are encoded here, visualized in this depiction. So you see a lot of dark, it's unknown, black, but you see also yellow, for example, you see green, blue, on the smaller areas are blue. More important are the yellow areas. Net, BA for Canada and US, North America. And yeah, it's also a way to the internet. This one became quite famous. It's a map of the Facebook connections in December 2010. It's also a telecommunications flow map with real-world point location. And of course, it's a bit difficult to see China here because China is not well connected with Facebook. You have your own software, own social networks that are not included in this map. Also Russia, here is Moscow, so there are links, but compared to the rest of Europe, for example, it's also quite weak here. Or another one, this is active and pending undersea cables around Africa. So it's also telecommunications flow map, also a network flow map, depicting qualitative and quantitative data with real-world point location. So you see here the different undersea cables, and the width of the line tells us something about the bandwidth for the connections. So how many gigabits can get through these cables. So most are here around sub-Saharan Africa. Sub-Saharan means, in fact, it's south of the Sahara region, the Sahara Desert, which is not entirely true, as there are other connections to there. But the cable were mainly established for this region that is south of the Sahara. As you see here are most of the connections. And there are also these Mediterranean undersea cables. Here is the Mediterranean Sea between Europe, Africa, and the Middle East. So again, you have color U for qualitative information. That's the name of the different cables. And the width of the lines is about the quantitative information. Now, the last topic I want to talk about today are cartograms. And cartograms are maps that purposely distort geographic space based on values of a theme. So that's a bit a strange idea at the beginning, but I hope you will be more familiar with that after this section. So it is, in fact, about attribute data that is used instead of the geographic data. But the geographic data, of course, also plays a role as a reference quantity, let's say. Making the size of countries proportional to their population is one typical example. You will see numerous examples later on. First, a bit of the theory. There are two main types of cartograms: line cartograms and area cartograms. First, line cartograms, they often use time instead of real-world distances. This is the typical application for line cartograms. For example, traveling time between metro or train stations, or flight durations between cities. Usually such line cartograms work very well because the time between and order of stations is more important than the actual distance between them. Remember the famous tube map of Harry Beck, the London Tube, London subway map. He rearranged this map. He made it, in fact, more abstract, but it didn't matter for the people who used the map, because if you are sitting in a subway or a metro line and traveling across a city, it's not important for you where exactly you are. You just need to know which station or in between which stations you are and where you can change trains. Of course, you have a rough idea where you are within the city, otherwise you would get lost, but you don't need exact locations. And therefore, you can also use time instead of the real-world distance. And the traveling time here is, in fact, more useful than the real-world distance. So we do not care how many meters two stations are from each other when we're sitting in the subway, but we do care about the time we need to travel from one station to the next. Therefore, this is a very useful approach for subway maps, for example. An interesting application are maps that show how space seems to shrink based on shortened travel times. So you can say this are kind of visualizations of the global village metaphor. You will also see examples for that. First, an example from the London Tube, the subway in London. Here you see a map with the travel times from one station, the Elephant and Castle station, which is somewhere here. And then you have the travel times, and you have these isochrones. These lines are called isochrones. That means these are lines with the same duration for your travel, so it's the same traveling time. And here is a section of this map. This is the station, the Elephant Castle station. So this is point 0 here. And here you see it's 5 minutes, 10 minutes, 15 minutes, 20 minutes. So all the lines have a 5-minute step. And so you can see how long you travel within the system here. And of course, therefore, you have not a scale that refers to the distance, the physical distance, the spatial distance. This is about the time difference, time distance. So you have a scale in minutes. Here, a distance in the map refers to a distance in time, not in space. Or here now, this is a general map, so it's not computed from one station, the traveling time, but it's just a map where the stations, their distance is just based on the traveling time. Again, enlarged section of this map, so you don't have the isochrones here because you cannot compute them for all stations at the same time. This map is a general one. And of course, you have also the scale. So you can measure here, this distance here. For example, let's say it's similar to this distance. This means traveling time 2 minutes. Or here another one. This is also about London. The geographic tube map first. So here it's based on the distance, therefore on the spatial distance. Therefore we have kilometers here, like in a normal map. And now this is based on traveling time. Now we have minutes here, not kilometers. And we have these circles. Obviously, one circle here is 10 minutes. And then you can click on one of the stations, for example, Arsenal station, and then this station is in the center, and so the whole network is rearranged, and you see how long you travel along the different lines. Or here you can also click or use mouse over effect. So from Arsenal station here in the center, you need 15 minutes to Piccadilly Circus, this station here. And this is also reflected, of course, in the time scale. So here you have 10, and then half of the next ring, 5, so you have 15 minutes. Then you get these nice trees if you take or you choose one of the stations that are far outside. So this is from Heathrow Terminals, the largest airport of London. It's now in the center, and you have the traveling time to all the other stations in the network. So to the center, Piccadilly Circus is one of the central stations. You need about 40 minutes. Or another one that's a similar one to the last one, but different city. This is now in the United States. This is the Washington Metro Travel Time Distortion Map. And here you have all the stations, and you can click on them. So they are organized alphabetically here, so it's easier to find them. And now if you click, for example, Federal Triangle, then Federal Triangle is here in the center. So it does not work so well with the annotation because text is here shown one over another, so it's a bit hard to read. But the idea is very similar to the last one. And yeah, you can here jump to different stations. If you choose one that's far outside the center, you get this palm tree-like situation, like before with the Heathrow terminals. Interesting here is that you can also click on certain keys in the keyboard. You can get different kinds of visualizations. So here, pressing, for example, number 7, you get a rearranged network that looks like that. If it's useful, it's another question. At least it's nice looking. You have the circles here in the background, these gray circles. This is about the traveling time. And yes, it's another idea that you can rearrange the network to certain patterns or personal preferences. And here now these examples about the global village metaphor. So maybe you've seen such maps before. This is the normal geography, the normal map of Europe. So you have no time distortion here. But then here, this is about the effect of introducing high-speed trains to Europe. This is 1993, and this would be maybe in 2020. Of course, these examples are older. So this was just something maybe they hoped. In fact, we have not the situation now in the year 2020. And yeah, you see, for example, here, Southeast Europe, there was not much change. So the first high-speed trains were obviously not introduced in this area. There, the trains are still very slow, and there is not much change today. So we are far away from that situation in Europe. But the idea was also to introduce high-speed trains in this area. Here you see a big difference. But yeah, it was just a plan or an idea. It's not what really happened. This might look as if these maps are based on some area distortions, but in fact, it's based on lines. So these are still examples about line cartograms, not area cartograms. This is another one, a better looking one. This is just France. And in the background, you have the normal map of France. A bit of it you can see. And of course, the main high speed is also about high speed connections. The most important is a north-south connection running here via Lille, Paris, Lyon, and Marseille. So here is the strongest reduction of traveling time, and therefore the distortions are strongest. Here you have Marseille in the background, and here you have it in the distorted map. And again, you have a scale here that refers to time. This means 1 hour, what is written here. And then the larger group, you can see them more often, are area cartograms. So these are the most common form of cartograms. They are created by scaling, sizing enumeration units as a function of the values of an attribute associated with the enumeration units. There are many algorithms that are used for this that have been developed. If you're interested in algorithms, you find a list at Wikipedia, the English version. Just follow this link. There are two main groups. The first one are contiguous cartograms. Here, contiguity of enumeration units is preserved, but not their shapes, which are greatly distorted. And the second are the non-contiguous cartograms. Here, shapes of enumeration units are preserved, but there are gaps between the units. So you cannot have both. You cannot have contiguity and preservation of shape at the same time. So one time you have preservation of the contiguity, and one time you have the preservation of the shape. To show you an example here about these two ideas, here you have the state of California with all its counties, and this would be a contiguous catogram of the same area based on the population. So areas where many people live, here Los Angeles, are greatly enlarged. So this is Los Angeles now, because this is proportional to the population. And there are other areas that are relatively large here, but there are not so many people live because it's a desert area. For example, that area here, I don't know the county's name, but it's quite small here, just this little area. And here is the bay, the California Bay, the San Francisco Bay, sorry, the San Francisco Bay. This is the city of San Francisco here, which is this area in the geographic map. So this is contiguous catogram. That means it's continuous. All the counties are connected, like they're connected in the original, but their shapes are distorted. It's not the same shape. The other one is the non-contiguous catogram. So we have the same area, the counties of California. Then you can resize the areas. So you enlarge the areas with high population, and you shrink, you make smaller the areas with low population. Then you would get this, but this is awful looking. So you separate the different counties from each other, and then you get this non-overlapping, non-contiguous catogram. And as you see now, the shape is preserved. So here you have LA, Los Angeles. The shape is the same, but it's larger. And at the same time, you have these gaps in between. So this is a non-contiguous catogram. Another form, kind of special form of an area catogram, is the so-called Dawling catogram. A Dawling catogram maintains neither shape, topology, nor object centroids, but still it is a very effective catogram. It's a bit like a diagram, you can say. Instead of enlarging or shrinking the units themselves, they are replaced with uniform shapes, usually circles, of the appropriate size. The algorithm moves the shapes till they only contact each other. So there's no overlapping, just contact between the different areas. Another Dawling-like catogram is the Demers catogram, which uses squares instead of circles. You will see that in the example. Again, it's about the counties of California and population. And the Demers catogram uses squares, and the Dawling catogram uses circles. And if you compare the two, you clearly see that in this situation here, the Demers catogram works better because the overall shape of California is better preserved. And even here, the San Francisco Bay is included, which is important for our orientation. So here, this area can clearly be identified easily, which is much more difficult here. Here it's clear this number 11 is San Francisco, but here, if you just see this map, it's very difficult to say that number 11 is San Francisco, because this Bay area helps us a lot to orient ourselves within the state of California. There are many examples here. I want to go through them quickly. You can check them out if you want by yourself. So this is about the world population. Each square means 500,000 people. This is a not entirely contiguous catogram. So some areas, the connections between the countries are preserved. For some, it was not possible. For example, here, Vietnam, of course, has a border with China, but it's quite far away from China. So it was not possible to preserve it in that way, as the shapes have the priority for the preservance here, and therefore it's not totally contiguous. It's impossible. And it's important to say, if you use population for an area cartogram, to get then is a map with the same population density everywhere, because always the same size of area represents a constant exact number of people. Therefore, the density, population density in this map is everywhere the same. That's a basic idea of area cartogram. That one here, it's also a bit funny, but also interesting. So the population of China, and you see a lot of different countries here that you could add together. All these different countries add together gives the population of China. But it's the same principle here with the grid system, and each grid cell represents a certain amount of people. This is about AIDS virus. You see the big problem here in sub-Saharan Africa. So this small area here, this is Northern Africa, and this is the whole rest of Africa. Yeah, there are many more examples. This is about population and GDP. This is about the earthquakes, and where the population areas, the highly populated areas, are in red here. So we have the risk of the high risk areas and the high population areas together. But this one is about the university ranking. It's also interesting. Yes. I want to stop here. Time is running out, and we will continue next week. Thank you for your interest, and I hope you have an interesting week, and hope to meet all of you again next week. And of course, again, please let me know if you have any troubles, if you don't understand what's going on, if you need some help, if you have any questions, then please contact me. So thank you for today. Have a nice day. Bye-bye.